In 2012, a single server failure brought down Netflix, causing a major outage and impacting millions of users. Distributed systems solve this problem by offering fault tolerance. If one node fails, others take over. They provide scalability, handling more traffic by adding nodes. They also reduce latency by serving users from geographically closer locations. However, this comes with challenges like network partitions, data consistency, and coordinating actions across machines. Companies like Google, Amazon, and Netflix run entirely on distributed systems, making this knowledge critical for any software engineer. The CAP theorem is a fundamental concept in distributed system design. It states that you can only pick two out of three: consistency, availability, and partition tolerance. Consistency means all nodes see the same data at the same time. Availability means every request gets a response, success or failure. Partition tolerance is a must-have in distributed systems, so the real trade-off is between consistency and availability. A CP system prioritizes consistency. If a partition occurs, the system might refuse writes to maintain consistency, like in a banking system where double spending must be prevented. An AP system prioritizes availability. During a partition, the system continues to accept writes, potentially leading to inconsistent data, which is acceptable for social media feeds. Remember the millions of users impacted by the Netflix outage? Consistency models define how data is made consistent across replicas. Strong consistency guarantees that a read operation will return the most recent write. Eventual consistency guarantees that if no new updates are made to a given data item, eventually all accesses to that item will return the last updated value. Causal consistency preserves cause and effect relationships. Amazon S3, for example, uses eventual consistency for new objects. This means that immediately after creating an object, reading it might return a 404 error. However, after a short period, the object will be available. The trade-off here is speed versus immediate consistency. Eventual consistency allows S3 to scale massively and provide low latency writes. Your interviewer will push back here. Why not always use strong consistency? The reason is that strong consistency requires more coordination between nodes, increasing latency and reducing throughput. Replication strategies determine how data is copied across multiple nodes. In primary replica, master-slave replication, writes go to the primary and reads can be served from replicas. In multi-primary, multi-master replication, writes can go to any primary, requiring conflict resolution. MySQL uses primary replica replication. Cassandra uses multi-primary replication. Synchronous replication guarantees strong consistency, but increases latency because all replicas must acknowledge a write before it's considered successful. Sharding, also known as partitioning, is essential when a single database can't handle the load. Imagine a single database trying to store 1 billion records. It's impossible. Sharding splits the data across multiple nodes. Common sharding strategies include hash-based sharding, range-based sharding, and geographic sharding. Hash-based sharding uses a hash function, like murmur hash, to determine which shard a record belongs to. Range-based sharding assigns records to shards based on a range of values. Geographic sharding stores data closer to users based on their location. Consistent hashing ensures that only kn keys need to be remapped when a node is added or removed, where k is the total number of keys and n is the number of nodes. This minimizes disruption. It's like seats around a circular table. When someone leaves, only their neighbors shift. However, sharding introduces challenges like cross-shard queries, hotspots, and rebalancing. Cross-shard queries require querying multiple shards to retrieve data. Hotspots occur when a single shard receives a disproportionate amount of traffic. Load balancing distributes incoming requests across multiple servers. Common load balancing algorithms include round-robin, least connections, and IP hash. Round-robin distributes requests evenly across servers. Least connections routes request to the server with the fewest active connections. IP hash routes requests based on the client's IP address, ensuring sticky sessions. Consensus algorithms ensure that multiple nodes agree on a value. This is crucial for leader election and commit logs. Raft is a leader-based consensus algorithm that uses log replication. In Raft, nodes vote to elect a leader. The leader appends entries to its log and replicates them to followers. An entry is committed when a majority of followers acknowledge it. Imagine a cluster of 5 nodes. To achieve consensus, you need a majority, which is 3 nodes. ETRED and Consul use Raft for distributed coordination. An experienced interviewer will probe, what happens if the leader fails? The key insight is that the remaining nodes start a new election to choose a new leader. Distributed transactions ensure ACID properties: atomicity, consistency, isolation, and durability. Two-phase commit, 2PC, is a common protocol. It involves a prepare phase and a commit phase. The coordinator sends a prepare message to all participants. Participants vote to commit or abort. The coordinator then sends a commit or abort message based on the votes. However, 2PC has a major problem. If the coordinator fails, the transaction blocks.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.